Welcome back to The Explainer. Today, we're totally bypassing the surface-level summaries to map out the actual physical mechanics of the global energy transition. We're going to dive deep into Alberta's comprehensive hydrogen strategy together. We'll be tracing the blueprint from foundational molecular chemistry all the way up to its future as a multi-billion-dollar global export powerhouse. This is exactly where hardcore engineering meets macroeconomics.
So here's our roadmap for today. We'll hit the science of hydrogen, check out the current hydrogen economy, dive into engineering the blue transition, map out infrastructure and local demand, and wrap up with the global export opportunity. Let's get into it.
Part 1. The science of hydrogen. To really grasp the economics here, we first need to understand why this specific molecule matters so much for decarbonization.
Now, the chemical contrast here is absolutely stark. Traditional hydrocarbon combustion, like burning methane, inevitably produces carbon dioxide, which is obviously a major greenhouse gas. But hydrogen combustion, it's beautifully simple. Combining hydrogen and oxygen yields literally zero emissions. The only byproduct is pure water vapor. Plus, hydrogen packs roughly 142 megajoules per kilogram on a higher heating value basis. To put that into perspective, that is basically 3 times the energy density of standard diesel or gasoline. It's this extreme energy density that makes it the absolute prime candidate for heavy-duty applications. When experts talk about hard-to-abate sectors, that specific math is exactly why hydrogen is at the very top of the list.
Look, we all know battery electrification is fantastic for your daily commute, right? But it hits absolute physical limits in heavy transport. For a battery electric semi-truck to actually achieve long-haul ranges, the battery pack has to be massive, and that extreme weight directly subtracts from the legal cargo payload the truck is allowed to carry. It fundamentally kills the commercial viability of the route. Hydrogen fuel cell vehicles bypass this entirely because the fuel and storage tanks are significantly lighter, so you maintain that crucial payload potential. And for aviation and maritime shipping, the weight and volume limits of batteries, combined with those massive recharging downtimes, make electrification pretty much impossible. They absolutely require a high-density zero-emission fuel molecule just to get across oceans and skies.
So instead of just burning it, heavy transportation utilizes this incredibly elegant electrochemical process inside a fuel cell. First, pressurized hydrogen gas enters from a carbon fiber tank, while outside oxygen gets pulled into the cathode. The magic really happens when a platinum catalyst strips the hydrogen atoms into positive protons and negative electrons. An electrolyte membrane then acts as a barrier. It lets the protons pass right through but completely blocks the electrons. Because they can't cross that membrane, those electrons are forced to take a detour through an external wire, and that detour is the exact electricity that physically spins the motor. Finally, the electrons, protons, and oxygen all reunite to exit the tailpipe purely as water. It's just an ingenious way to extract massive power without a single carbon emission.
Moving on to Part 2, the current hydrogen economy. Let's establish the baseline we're actually starting from. Take a second to really absorb this number. 2.6 million tons. That is Alberta's current existing annual hydrogen production. It's a staggering industrial footprint, making up a massive 65% of Canada's entire national hydrogen share. So Alberta isn't starting from scratch here. It already possesses one of the most sophisticated hydrogen ecosystems on the planet. But here's the catch. Where is all this gas actually going? Right now, virtually none of it is used for transportation. 100% of it is captive as a local industrial feedstock. 62% is consumed directly by the energy sector for bitumen upgrading, basically adding hydrogen to heavy crude, while the other 38% goes into the chemical sector to synthesize ammonia for fertilizers. So today, it's strictly an industrial commodity, completely absorbed by existing local supply chains.
Now, a super common question is, well, why don't we just mandate green hydrogen immediately using wind and solar? Honestly, it comes down to stark economics. Gray hydrogen, which is produced from natural gas, currently costs between $1 and $2 per kilogram. Green hydrogen requires massive amounts of low-carbon electricity, roughly 50 to 55 kilowatt-hours for every single kilogram produced. In our current grid landscape, that pushes costs way up to $4 and $6 per kilogram. You simply cannot force an overnight 300% cost increase on foundational agricultural and energy sectors without causing severe economic consequences. A transitional bridge is absolutely required to keep these industries functioning while emissions drop.
Which brings us to Part 3, engineering the blue transition. If we can't affordably switch to green electrolysis tomorrow, how do we decarbonize production today?
Let's look at the legacy technology.
Steam methane reforming, or SMR. It mixes natural gas and steam in a highly energy-intensive process that intrinsically produces CO2. Left unabated, SMR releases 10 to 14 kilograms of CO2 equivalent for every single kilogram of hydrogen. Even with advanced retrofits, carbon capture on SMR generally maxes out around 85%. The future state engineering is autothermal reforming, or ATR. ATR introduces pure oxygen into the mix, creating a self-heating reaction. But the real game changer? It generates a highly concentrated, high-pressure CO2 stream that routinely targets 95 to 99% capture rates. This fundamentally shifts hydrogen from a high-emission chemical to an ultra-low carbon energy carrier. That engineered leap is the entire crux of the transition strategy.
But capturing that carbon is really only half the battle. The other half? Geologic permanence. Without carbon capture and storage, or CCS, blue hydrogen is just a myth. Fortunately, the Western Canadian Sedimentary Basin offers world-class deep saline aquifers way down below the water table. These aquifers are trapped beneath impermeable rock layers, known as the seal, that have successfully contained high-pressure hydrocarbons for literally millions of years. This pore space provides a strictly regulated, permanent storage solution managed by the Alberta Energy Regulator to ensure that captured CO2 never re-enters the atmosphere.
And this isn't just some theoretical whiteboard exercise. Unprecedented capital is being deployed right now in Alberta's industrial heartland. We're talking about the Air Products Net Zero Complex. We're tracking Dow's US $7.5 billion Path to Zero project in Fort Saskatchewan to achieve net zero Scope 1 and 2 emissions, and Linde's building a $2 billion clean hydrogen facility utilizing that exact ATR technology we just talked about. Billions of dollars are already in motion to physically re-engineer the foundational chemistry of this entire economic region.
All right, Part 4. Infrastructure and local demand. How do we solve the domestic network problem?
It's the classic chicken and egg dilemma of any new energy paradigm. Think about it. Fleet operators absolutely will not invest millions in hydrogen fuel cell trucks if there are no reliable refueling stations on their routes. Conversely, energy companies are not going to drop millions building complex high-pressure hydrogen stations if there are no active fleets to actually buy the gas. So, how do we break this commercial gridlock?
The solution relies on highly coordinated, targeted commercial routing along the Western Canada corridor. Instead of trying to build stations everywhere all at once, the strategy focuses on primary arteries, like the massive freight corridor between Edmonton and Calgary. By guaranteeing fuel supply concurrently with fleet adoptions, initiatives like the 5,000 Hydrogen Vehicle Challenge aim to deploy thousands of heavy-duty fuel cell trucks and buses. Under high-support scenarios, we could see up to 8,000 hydrogen vehicles operating on these focused routes by 2040. It's all about proving commercial viability before expanding the footprint.
We're also seeing this localized demand scale rapidly within concentrated industrial hubs, like the Edmonton International Airport's YEG Living Lab. They are actively operating mobile refueling units, deploying 100-vehicle fuel cell fleets, and even piloting hydrogen-diesel blended equipment. Furthermore, clean hydrogen serves as a vital feedstock for producing synthetic e-fuels, which offers a highly sought-after pathway for sustainable aviation fuel. This concentrated demand basically proves the technology at commercial scale in a closed, highly visible environment.
Finally, Part 5, the global export opportunity, scaling from local abundance all the way to the Indo-Pacific.
If we map out the long-term trajectory, the growth curve is just wild. From our current baseline of 2.6 million tons, which, remember, is entirely for local use, production is expected to scale to 4.4 million by 2034 as those megaprojects wrap up. But by 2050, the roadmap envisions a staggering 10 million tons per year dedicated specifically to clean exports. To bridge those massive ocean distances efficiently, this gaseous hydrogen will largely be converted into ammonia. It's a highly stable, dense carrier molecule that is perfectly suited for global marine transport.
Now, why scale so massively? It is completely driven by the strategic energy deficits in the Indo-Pacific. Highly industrialized, densely populated nations like Japan and South Korea face severe geographic limits on their own renewable energy generation. They absolutely require massive, secure imports of low-carbon molecules to hit their net zero 2050 goals. Japan actually plans to co-fire ammonia in existing thermal power plants to rapidly slash coal emissions. Meanwhile, South Korea expects an 80% import reliance for its clean hydrogen supply. Alberta is positioning itself to be that secure, geopolitically stable energy partner, fueling this entire Asian industrial transition. But of course, none of this transformation happens purely on free market goodwill. It requires strict fiscal mechanics to de-risk these massive capital requirements. The Federal Clean Hydrogen Investment Tax Credit offers up to 40% back on eligible equipment. But the real genius is the emissions kicker. To get that top-tier payout, projects have to rigorously prove a life cycle carbon intensity below 0.75 kilograms of CO2 equivalent per kilogram of hydrogen. That single, aggressive metric actively forces the industry to abandon dirty SMR and invest entirely in high-capture ATR and electrolysis. Combined with provincial programs, this is literally policy dictating physical engineering.
So as we wrap up this explainer, I want to leave you with a question to chew on. We've mapped out how a single jurisdiction is leveraging deep geology, advanced chemistry, and billions in capital to completely re-engineer an industrial commodity into a zero-emission global fuel export. If a transition of this immense scale and complexity is actively unfolding right now, what are the true limits of our broader global energy transition? And what role will molecules like hydrogen play in reshaping geopolitics and energy security over the next 20 years? Thanks for exploring this with me, and I'll see you in the next deep dive.